In this video, we will be describing some of the various shapes that atomic orbitals take in modern quantum mechanics. As mentioned in previous videos, electrons do not actually follow an orbital path as described by the Bohr model. In modern quantum mechanics, the way that we describe where the electron is located is in terms of probability distributions. The orbitals that we will be showing in this video are representations of the probability of finding an electron in a region of space. The outer shell, or the surface of the orbitals that we will be showing, represent the maximal probability location in three-dimensional space. The simplest orbital is the s orbital. For these, L is equal to 0. Each one of our principal energy levels, which is represented by the n quantum number, has the ability to have an s orbital. If you remember back to our limits on the possible values for our four principal quantum numbers, n can be any integer value starting at 1, going up to infinity, counting up in integers. L starts out at 0 and counts up to n minus 1. So if n, our principal quantum number, is equal to 1, then L would be equal to 0. It is for this reason that each one of our principal energy levels, again represented by n, will have an s orbital. So if n is equal to 1, we will have an s orbital. If we're on the n equals 2 principal energy level, we still have an s orbital. If we're on the n equals 3 principal energy level, we have an s orbital. The s orbital will be the lowest energy orbital for any given principal energy state. So for any one of our different n values, the s orbital will always be the lowest energy orbital. It has a spherical shape and will have n minus 1 nodes. The nodes that you will see are spherical nodes. So if we were looking at the 2s orbital, n would be equal to 2, and so we would have 2 minus 1, or 1 node. What that would be represented as in terms of an orbital is you'd still have the spherical outer shell, and then in a region in space you would have a shell that has no probability of finding the electron, and then inside of that you would again have a probability of finding the electron. The second lowest energy orbital are the p orbitals. This is when L is equal to 1. In order for L to be equal to 1, you must be at the n equals 2 or higher, because again, your L values range from 0 to n minus 1. So in order for you to have p orbitals where L is equal to 1, your n has to be at least 2. So each principal energy level above n equals 1, so 2 and higher, will have 3 different p orbitals. The reason that there are 3 p orbitals is that the m sub L value describes the different suborbitals that you can have. And the m sub L values can range from negative L to positive L, going through 0 in integer values. Each one of the p orbitals will point along a different axis. You have the px, the py, and the pz. These correspond to the negative 1, 0, and plus 1 values for m sub L. The p orbitals themselves again are the second lowest energy orbitals for a given principal energy state. The L equals 0, the s orbitals are the lowest. The L equals 1, the p orbitals are the second lowest. The shape of these is sort of a dumbbell shape where you have 2 large lobes, and in between them you have a node. The node is where the nucleus is, and it is planar in nature, meaning that if we're looking at the p sub x orbital, that there is a plane, the yz plane, that cuts through the orbital, and along that entire plane the probability of finding an electron in the px orbital is 0. The electron cannot be located anywhere along our yz plane. Same thing occurs for the py orbital, except this time it's the xz plane, and for the pz orbital it's along the xy plane. So the subscript on the orbital name, the px, the py, and the pz, describe which axes the orbital lies along. So the pz is along the z-axis, the py is along the y-axis, and the px is along the x-axis. The next series of orbitals are the d orbitals, for which L is equal to 2. Because L needs to be 2 for you to have d orbitals, the lowest principal energy state would be 3. So each principal energy state above n equals 2, so above not including n is equal to 2, will have 5 d orbitals. The d orbitals correspond to m sub L values of -2, -1, 0, +1, and +2. 4 of the orbitals are going to be aligned along different planes. The fifth is aligned along the z-axis. So you have the dxy, the dyz, the dxz, the dx squared minus y squared, and the dz squared. The first 4 are going to have this 4-lobed shape, which looks much like an X, which will have 2 planar nodes which bisect the orbitals. The last of the d orbitals, the dz squared, has 2 lobes that look very much like a p orbital with a ringed collar called a toroid that goes around the orbital. We will actually look at these in the next slide. For the higher principal levels, where n is 4 and higher, you will have additional spherical nodes, just like you had with the s and the p orbitals. So the shapes of the d orbitals, again, have this X-like configuration with 2 planar nodes between them. So the planar node for the dyz cuts across here and cuts down here. So the planes that bisect the orbitals are along the xz plane and along the xy plane. The dxy looks the same as our dyz, except it is rotated, so it is lying along the xy plane. The lobes themselves are located in between the axes. They do not lie on the axes. Same with the dxz. It falls along the xz plane with the lobes being located between the axes. For the dx squared minus y squared, you have an X shape, but now the orbitals lie along the y-axis and the x-axis. The last one, which is the dz squared, has a p orbital shape with this turboid ring that goes around the center. The last of the orbitals that we will be regularly working with are the f orbitals, where L is equal to 3. There are theoretical orbitals, the g, h, and I orbitals, but in general the periodic table does not extend far enough to make use of these orbitals. Because these occur for the L is equal to 3, and the L values range from 0 to n minus 1, in order for us to have an L equaling 3, our minimum n value of our principal quantum number has to be 4. So for each principal energy state above, and again not including 3, we'll have 7 different f orbitals. The f orbitals correlate to m sub L values of -3, -2, -1, 0, +1, +2, and +3. Again, your m sub L values range from -L to +L, moving in integer values and containing 0 in between. The f orbitals are fairly complex. They comprise mainly of 8-lobed orbitals that contain 3 planar nodes that bisect them. There are, however, a couple that have 2-lobed orbitals that look somewhat like p orbitals, again with our ring collar turboid sections in them. The f orbitals all have planar nodes, and the higher principal levels will also have spherical nodes. So for our n equals 5 and higher, you will have spherical nodes which are located within the f orbitals. Here are illustrations of the f orbitals. The top 3 are those that have the p-like orbitals with 2 turboids around them. The bottom 4 are the ones that have the 8 lobes that kind of look like two series of X's. So they will have three sets of planar nodes that bisect them. One, if we're looking at the F sub XYZ, you'll have a node along the YZ plane, you'll have one along the YX plane, and the last one is the XZ plane, which will bisect the lobes. Those are regions where there is a zero probability of finding an electron. The orbitals that were shown in the previous slides are determined from mathematical wave functions. An example of a wave function is a sine function, which starts out at 0 at x equals 0. Because the sine function itself can extend both in the positive and negative direction, our wave function can have both positive and negative values. If we have a wave function that has a node in the middle, this is a location where on the left side it will fluctuate up and down, and the right side will fluctuate up and down, but at the node it maintains at the axes with a value of 0. Our orbitals can also have these nodes. These nodes are where the wave function is equal to 0. The node, because it's a set location that doesn't fluctuate up and down, this represents the location where the phase or the sign of our wave equation goes from positive to negative or negative to positive. So the nodes are where we have a change in the sign or a change in the phase of our wave function. When orbitals interact, their wave functions may be either in phase, having the same sign, or out of phase. If the wave functions are in the same phase, they will undergo constructive interference, becoming larger and having an additive effect. If the phases are misaligned, meaning that you have a positive phase from one orbital and a negative phase from the other orbital, they will destructively interfere, and this can lead to lack of interaction or non-bonding between orbitals, as we will see in later videos.